Afternoon, everybody. I'm Ivan Deutsch from the University of New Mexico, so hope everyone's nice and warmed up now here in lovely Tucson. It's a great pleasure for me to be here, and I want to thank the organizers for putting this lovely new event together, and we'll see the precedents that we can set. Before I get started, I'm just kind of curious, just to get a little bit of the lay of the land here of the audience. How many of you are undergraduates? How many of you are first-year graduate students? Second? And third and beyond? Okay, so we have a fair, yeah, you too, definitely beyond. Right, so I hope there's enough here for everyone, and I really want to engage you in a conversation, so please interrupt me and let's discuss anything that you'd like to discuss that for further clarification. So I'm privileged enough to have been preceded by some really excellent talks that really set the stage for my lecture today, which is about quantum control and measurement of atomic spins. So here's the basic syllabus for the two lectures. In the first lecture, I'll talk about some general things about quantum control theory and the kind of atomic physics that is being used in the kind of control that we're going to apply. And in the second lecture, I will talk about the other half of this. As June said, measurement and control are two sides of the same coin. And so I'll talk about quantum measurement theory and hopefully get to talk about quantum tomography in this context as well. And this work has been discussed in two long review articles that we've recently published. So I'm not going to be sprinkling references all over the place. These are very heavily referenced papers, so you can find all of the reference to a lot of the primary literature in there. And I also wanted to draw your attention to this talk. In some sense, you'll be able to get a little bit of reinforcement on these topics because Professor Jessen is going to give his set of lectures next week on work that much of the same kinds of topics, much of which we've done in collaboration. All right? So, and of course these will be posted on the web, so all the references and stuff will be there as well. All right, so let's get started. When we think about control, well, let's think about what is control classically. In an engineering context, you have some control system you want to guide, for example, your airplane. You better hope there's good control of your airplane. And control theorists, even in the engineering context, the engineers have theorists too, have developed a whole mathematical structure in thinking about that. And generally, they think about this in terms of a kind of feedback control. That's one paradigm for control. We can also think about an open loop control kind of context. And this is from Google Maps. This is my house. This is the Albuquerque airport. And somehow we need to get from the initial point to the target. Of course, Google Maps is thinking about prior information, what it knows about the traffic patterns in Albuquerque, and you might think the easiest way is to go down Montgomery and then down I-25, but in fact, it's faster to go all the way down to I-40 up and over, because it's using some notion about the dynamics in thinking about how you get from point A to point B. Of course, if I was bad and I looked at my iPhone while I was driving and saw the real-time traffic, which I do sometimes, I'm on tape, darn. Then I might adapt my path, and that would be adaptive control. But these are different paradigms that are used in, controlling classical systems. control means controlling systems whose dynamics are governed by the laws of quantum mechanics. And of course, well, at some level, everything is governed by the laws of quantum mechanics, but what we really mean by this is coherent part of quantum mechanics, the aspects that both June and Pierre talked about today. And for example, we might be controlling and probing matter on its natural timescales, and the kind of tools that are necessary to do so that we heard about from June this morning in terms of the tremendous progress in the development and control of light sources that can control molecular vibrations, or, for example, looking at the motion of an electron cloud inside an atom, and thereby measuring it and controlling it. This is one, the ultra-fast is one very important aspect in quantum control science. We also heard about, in fact, this was great, I had these slides prepared and it just worked out just perfectly. We heard from Pierre this morning about a different realm in which we are now being able to control quantum systems based on optomechanics and the coupling of the quantum vibrational motion of matter to the quantum fluctuations of light. Here's another regime where we really want to be able to control quantum systems. Yet another motivation, the one that I'm particularly most interested in these days, or have been for quite a while, is taking the tools of quantum control to apply them to do things that nature never contemplated at all, like computing quantum information processing. And perhaps the leading platform for doing so is an AMO platform. Ion traps have made tremendous strides in quantum information processing. And we have some kind of perhaps quantum circuit. We want to do this in the most controlled way to run a quantum algorithm. So this is our motivation, and what I'm going to be talking about in these series of lectures is a particular platform as kind of test bed for doing quantum control. And that test bed is based on controlling atomic spins. And atomic spins are, in some sense, a very natural carrier of quantum information because of the long coherence times and the plethora of coherent control tools that exist in more of the RF microwave regime. I mean, we're now moving into the optical regime through these frequency combs, but at its base, the sort of foundation of this has been spin control, and be that the nuclear spins in liquid state NMR, or spintronics, and quite often in atoms, in atom traps, it's the qubits or the quantum information are stored in the atomic spins. So we want to use these as a platform for exploring quantum control. All right. So let's get started. I want to just begin at a very fundamental level. This is an AMO school, so I want to remind you of some fundamental atomic physics here. So what the particular atoms we're going to be looking at are alkali atoms, although much of the same physics applies. It doesn't really matter they're alkali, but let's just consider that case. So we're going to be thinking about their atoms in their electronic ground states, in which case the degrees of freedom that we're going to be controlling and manipulating are the spin degrees of freedom, and they involve both the electron, in this case the single valence electron, coupled with the nuclear spin. And as you remember, when these get coupled together, you get a total angular momentum, in this case equal to I plus a half or I minus a half. And that that corresponds to a Hilbert space in which we can think about that either in the uncoupled representation of electron spin and nuclear spin, or we can think about it as two subspaces, the irreducible representations, total angular momentum, F plus and F minus. These are not the raising and lowering operators, these are just denoting F plus and minus here. So the total dimension of my Hilbert space that is going to be our kind of playground in which we're going to be able to work in and do our control involves twice the total number of magnetic sublevels in the nuclear spin. So for example, and so of course the spins are coupled together here through, in this case, through the contact interaction, gives rise to the hyperfine interaction here, in which the good quantum number is now the total angular momentum F. And for the case of cesium, which is what is the atom that worked on in Paul Yessen's lab, the nuclear spin is 7/2, giving rise to a total angular momentum F equals 4, F equals 3, and a total Hilbert space of 16 dimensions. So our goal will ultimately be to be able to do arbitrary control and measurement within this 16-dimensional Hilbert space. Okay? All right, so that's sort of the base, that's our Hamiltonian, and we're going to control it. We need to think about the physics through which we can interact with these spins. And so let's review that a little bit. So the basic, when you think about a spin, the basic interaction that you imagine is interacting the magnetic moment with a magnetic field. And we have in general both nuclear and electron contributions of this. This is typically ignored. If we want to do very precise control, we better include that in our discussion as well. And the total Hamiltonian involving both the hyperfine and the magnetic interaction then, well, we can look at that in a few different regimes. If the magnetic interaction is a small energy compared to the strength of the hyperfine interaction, then we can do perturbation theory. And if we restrict ourselves to a given total angular momentum manifold, then you remember the Landé projection theory says that we can project this interaction onto that space with that total angular momentum F, and then we have an effective G factor, the Landé G factor associated with that F. Okay? It's important atomic physics to remember. So we might think about higher or second order corrections. There may be a quadratic effect that if we have a strong enough magnetic field compared to the hyperfine splitting, we might need to worry about that. But what the effect is, if this was my original Hilbert space, then the effect of the Zeeman interaction here, if we take the quantization axis to be the direction of the magnetic field, is to split out these levels in the following way. And they split in opposite directions because the G factors have opposite signs. And they're about equal and opposite. There's a small correction due to the nuclear spin, but if we ignore this, then this splitting is equal to that splitting, but just equal and opposite. Okay, so that's one basic interaction. And what that interaction does, the interaction that corresponds to the coupling of the spin to the magnetic field, you remember, is a rotation. And so what we get is Larmor precession of the spin. And physically, this regime, the linear Zeeman regime, in which the hyperfine coupling is very big compared to the magnetic interaction, is one in which the nuclear spin and the electron spin are spinning extremely rapidly compared to the rate of Larmor precession of the total spin. So the two spins are coupled together and they're dragged together, and the total F is conserved. And the two different F's, the one corresponding to F equals I plus a half and F equals I minus a half, they precess in the opposite directions because their G factors are opposite signs. Now, we can further control these spins resonantly. So, for example, we could apply an oscillating magnetic field that oscillates at the Larmor precession frequency. Suppose we put on a strong bias field, we'll call this the z direction, and my spin in principle in this vector picture precesses around it. If I apply a field in the x or y plane that oscillates at the same frequency that the spin is precessing, then that's the basic paradigm of spin resonance. And even if this is a tiny amplitude, if it's the same frequency, then we get a resonant enhancement, and we'll get a flipping of the spin around the transverse field. In principle, if we oscillate linearly, we couple to both the co-rotating and counter-rotating pieces because this linearly oscillating field contains a component that rotates, co-rotates, and counter-rotates. That's the original meaning of the rotating wave approximation. It was an actual rotating wave. And it also means that if we actually have a rotating wave in the lab, physically rotating, then in principle, we could couple solely to either the upper manifold or the lower manifold, because only one will be co-rotating and the other will be counter-rotating. So in this picture that we had of the hyperfine coupling, we could, in principle, just Larmor precess, say, the upper and leave the lower one alone if we wanted to. What this means from the quantum mechanical point of view is that we put on the bias field that created the splitting of these levels. And then we have these oscillating magnetic fields in the transverse direction. Remember, they correspond to raising and lowering operators of the magnetic sublevels, and they couple then near resonance if this frequency is near to this Larmor precession frequency, couple the m plus or minus 1 levels. In addition, we could apply microwaves. This is another of the fundamental tools that we have at our disposal for controlling these spins. And so in cesium, this corresponds to 9.2 gigahertz. If we apply a microwave, which has a magnetic field that is oscillating near that frequency, and in fact, if we apply it at this frequency corresponding to the combination of the hyperfine resonance plus the Zeeman shift in the bias field, well, we would be resonant with this interaction. We would be off-resonant here and off-resonant here. Of course, all these other ones are also driven. Remember, you can change the magnetic sublevel by m equals plus or minus 1 or 0, depending on the polarization of your microwave. But if you don't have polarization control, you will have frequency resonance here, which would mean we would be primarily driven on this transition. And the effect then would be then to cause Rabi oscillations between these two levels in a coherent way, which you remember correspond. We can think about that in a kind of pseudo-spin picture, just like Larmor precession, but now this is not a real spin in 1/2, this is a pseudo-spin 1/2, corresponding to rotation on the Bloch sphere, where spin down corresponds to this magnetic sublevel, and spin up corresponds to that magnetic sublevel. So this is another one of our control tools that we have access to. So just to summarize this, what we have here, in terms of our magnetic interactions, we have the hyperfine interaction, which couples the nuclear and electron spin together. And then we have this magnetic interaction, which might have combinations of a quasi-static, I call it DC, but it might be slowly varying, resonant RF and microwave. And they correspond to Hamiltonians of this sort, where I've allowed myself the possibility of coupling the spins in both the x and y directions. All right? Does anybody have any questions so far? Yes?
Could you maybe explain again how different polarizations of light determine whether it's delta m equals plus minus 1 or 0?
Right. So in this case, this is not light, this is microwaves. It doesn't matter. It's the same physics. There are what we call selection rules. Okay? So the selection rules are determined by the nature of the multipole moment of the charge and current distribution that's interacting with your field. In this case, this is a magnetic dipole interaction. And the magnetic dipole interactions correspond to the vector dipole. And the vector dipole has 3 components. And so you can think about this component as the vector being parallel to the quantization axis. So this is the magnetic field oscillating along the bias. So if I had microwaves that were oscillating along the bias, they would drive this transition. If the bias was like this, and the magnetic field was oscillating like that, well, if it was oscillating like this, it would drive n equals plus 1, and if it was oscillating the other way, n equals minus 1. Anybody else have a question? Okay, so that's really the fundamental physics associated with the magnetic part, and that is the first thing you think about when if you thought about interacting with your spins. But there's another way we can interact with the spins, and that's based on light through the AC Stark shift. So let me quickly review a little bit of that. So our fundamental interaction, so here now we're talking about an electric dipole as opposed to a magnetic dipole. And if we had that on resonance, of course, what we're going to do is drive Rabi oscillations between the ground and excited states. That's not what we want to do. We want to keep in the electronic ground state, but just manipulate magnetic coherences with the light in a kind of magneto-optical way. But let's just begin by thinking about the two-level atom without the magnetic substructure. If I'm detuned from resonance, here I'm detuned below, we call that red detuning, then, well, we could do perturbation theory based on this interaction Hamiltonian, and the effect is a little bit of a tiny admixture of excited state with the ground state, assuming this detuning from resonance is huge compared to the coupling strength between the dipole and the electric field, the thing we call the Rabi frequency. And if you do perturbation theory, you find the ground state is shifted in second order, and that, you remember energy denominators from perturbation theory, and this is the shift. Now, we can understand that shift in a kind of classical way as the energy associated with a polarizable particle interacting with the field. If I have an induced dipole moment, then that induced dipole moment interacts with the electric field. And that is what we call the AC Stark shift or the light shift. And this polarizability, I've written it here as a tensor in terms of the dyadic of the dipole matrix elements relative to the detuning. That's a very important picture that we're going to build on now. But the picture you should sort of have in your mind here is, for this two-level atom is I've induced a dipole moment, and then that dipole moment tries to align itself with the field, and the energy due to that is what we call the AC Stark shift. Now, our atoms here are not two-level atoms. Bill Phillips was famous for saying sodium is not a two-level, no, there are no two-level atoms, and sodium is not one of them. And that was one of the famous reasons why we got the subdoppler laser cooling, which maybe we'll hear about later in the week. But the point here is that, here's say I want to control this manifold of magnetic sublevels. We have light, which in principle, say if it's tuned close enough to this f equals 3, the selection rules again are very similar to the magnetic dipole. These are electric dipole. And we have what we call pi and sigma plus, and we have to think about all the Pledge-Gordon coefficients and the oscillator strengths and all of the gritty atomic physics that tell us about how the light couples to each of these sublevels. In fact, we can do that. It's often what we do. But there's another picture of that that's extremely useful that I want to discuss now. And that's, forget about thinking about expressing the interaction in a basis, in a Hilbert space basis of magnetic sublevels. Let's think about these as operators without thinking about the magnetic sublevels themselves. So this is what we call the polarizability tensor, where now these are not matrix elements. I'm thinking about these as operators. Operators that go between the excited state and the ground state, or vice versa, from the ground state to the excited state. So, back on here, this is the projector onto this subspace and a projector onto that subspace, for example. So, now, this is a tensor, and maybe you've learned in your quantum mechanics class that when you think about tensors, it's useful, perhaps confusing, perhaps messy, or for reasons that we never understand why we do it, but it's extremely important physically, to think about these tensors from the point of view of so-called irreducible representation. So, this tensor, which is an outer product of two vectors, isn't a natural object that is preserved under rotation. It's useful to decompose this into a piece that is essentially a scalar, a piece that is essentially a vector. The scalar part is just the dot product between these two vectors. The vector part is the cross product between these two vectors. And then the part that's left over is what we call the irreducible second order rank tensor. So this is related to the trace of the matrix. This is the antisymmetric part of the matrix, and this is the symmetric traceless part of the matrix. Each one of those is an irreducible tensor. Now, why do they do that? It's just put up an equation that has nice words like scalar, vector, and tensor. Because the physics of the interaction between the light and the matter is dictated by these irreducible pieces. So, for example, let's look at our tensor again. But now, remember, I had the projectors, which were summed over everything. So I'm imagining now I am detuned big enough that I need to include some set of excited states. I might be detuned big compared to that hyperfine structure in the excited state. Or I might be detuned big maybe compared to the fine structure in the excited state. So I need to sum over all the possible virtual transitions that I can make into the excited state. That's a messy thing. However, if I start in a given ground state, then I'm not Rabi oscillating, then I'm going to stay in that ground state. In which case, I can remember we did this Landau projection theorem we did for the magnetic interaction. We could do the same kind of Landau projection theorem for this tensor. In which case, every tensor is some components of the total F. So there's a piece here that's a scalar that doesn't have anything to do with the magnetic sublevels. The vector part of interaction, the part that was the cross product, there's only one vector out there. The only vector is F. So it has to be proportional to F. Now it also has to be antisymmetric under exchange of the two indices. So this vector, this tensor, this antisymmetric tensor, is the only thing that's out there that is anisymmetric under those indices exchange and is proportional to F. It also has to be Hermitian, which is why there needs to be this I there. Otherwise, when you take the transpose, you don't get the conjugate. So, and then there's some coefficient out here, which is whatever depends on the atomic structure. And then finally, there's an irreducible rank 2 tensor piece, which is a symmetric traceless tensor. And this is the only thing there is out there. So just a priori, we can write down what the tensor has to be, just based on our intuition. And the dirt of the physics, then, is what are these coefficients? What is C0, what is C1, and C2? For that, I point you to Appendix A. And if you find a minus sign error in that, please tell me, because there is one buried in there and I've never found it. So, but anyway, okay. Anybody have a question about this? Because I'd like to explain it further if there's any questions. Okay, so this is our polarizability tensor. Why do I bother? Well, now we can see the physics associated with this interaction. So the scalar part here depends, remember, it was just something proportional to the identity matrix. It was a scalar. So it just depends on the total intensity of the light. It has nothing to do with the polarization of the light, and it has nothing to do with the magnetic sublevels of the atom. So in some sense, from the point of view of control, at least within a given manifold F, it's not relevant. The part, remember we have this epsilon ijk? That gives us the cross product between E and E star. And this is our vector term. And then we have this tensor term here, coupling things quadratically. I guess, I didn't actually find it. Something seems to be missing, but. Notice here, this term here looks like a fictitious magnetic field. Remember we had the magnetic interaction, which was B dot F? So this looks like some effective B, some effective pseudo-magnetic field that couples to the spin of the atoms. And that's the vector light shift. Then we have this tensor term. Okay, so now I have a quiz. If you're going to have a lecture, you've got to have a quiz. The atom that we're talking about here, we said, was in its ground state, right? And the ground state for cesium or alkalis is spherically symmetric S state. So the electron cloud is a sphere. And if we had something that was not a scalar polarizability, then if I push it in one direction, it's going to polarize in another direction. So why in the heck does that happen? And this thing, well, oh God, that's not a sphere. But it is on my screen. It's just widescreen. What do you guys think?
Can you repeat the question?
So the question is, let's go back. Epsilon ijk, or I'm sorry, alpha ij, is the polarizability tensor matrix. The fact that it's not just a number, but a matrix, means that, and a matrix that's not just a diagonal matrix, with the same elements on the diagonal, means that d dot alpha dot times E gives you a D, a dipole moment, in a different direction in the electric field. Which means that, I have this cloud of electron, I push on it with electric field, and it responds in another direction. But the electron cloud is symmetric, spherically symmetric. So where are we breaking symmetry here?
Coupling with the nuclear spin?
Excellent. So there's something about coupling of the charge to spins. Of course, we have other effects. It's not just electronic effects. We have spin effects that are built into our atomic structure. So the vector light shift can be understood, the physics of the vector light shift can be understood at its base being arising from the fact that we are coupling the orbit to the spin in the excited state. So because, in the excited state you have p orbitals coupled to spin degrees of freedom, means that different directions of the p orbitals give you different response. And that is fundamentally behind the vector light shift. Now, in the case of alkalis, our spin is spin 1/2, which means that the vector light shift can only give rise to a rotation, which is a rank 1 irreducible tensor. Okay? And so what that means is that when I detune this laser big compared to the excited state hyperfine splitting, I'm sorry, to the excited state fine structure splitting, number one, I lose this vector light shift, and I would only have a scalar term. I want to get to the hyperfine effect now, which was mentioned, the coupling to the nuclear spin. If I want to get something beyond rank 1, I need to involve the nuclear spins, because the nuclear spins have higher angular momentum. And that supports something beyond rotation. The spin 1/2, the only thing you can do is rotate it. But higher spins, you can do more than rotation. So if my detuning is not too big compared to the hyperfine splitting, another way of saying that is in the time domain. Remember, the amount of time, sort of loosely, the amount of time you spend in the excited state is inversely related to the detuning. If I'm detuned too big, then I don't stay in the excited state long enough, and there's not enough time for electron spin to couple to nuclear spin. But if I'm detuned close enough, well, then I can. And these physical pictures allow us to intuit what regimes we might want to operate in order to access different control tools. Because as we showed in the previous slide, there's the vector light shift gives us this fictitious magnetic field. If I want this fictitious magnetic field, well, then I better detune close enough compared to the fine structure. But if I want tensor terms of that, I detune close enough to the hyperfine structure. Okay. Right, so that was the point I wanted to make. I guess it was here on this slide. Notice that the amount of fictitious light shift depends on how circular or elliptical the polarization is. If I have linear polarization, well, then the polarization vector is real, and E cross E is 0. But if my polarization vector is a complex vector, then E star cross E is non-zero. So the amount of fictitious magnetic field depends on how circular it is. So pure circular polarization, the helicity, or you can think about this term as the spin of the photon coupling to the spin of the atom. And that gives rise to the vector particle light shift. The tensor light shift doesn't have such a simple picture. It's due to this virtual hyperfine nuclear spin coupling, blah, blah, blah. But the important point from the mathematics here is that this irreducible rank 2 part, you remember it had this kind of E dot F squared term in it, has a term that's proportional to some nonlinear term in a spin component. Of course, for a spin 1/2, that's the identity. It's a sigma matrices squared to 1. But for higher spin, that's interesting. Now, we do have light comes at a price, If you're detuning close enough to resonance, then of course you can get spontaneous emission. And so that is what we call photon scattering. The photons come in and they're scattered. And that will cause decoherence in the system. And so that's something, in principle, in terms of our control, if we're going to use the AC start shift as part of our control, then we better worry about that as well. And photon scattering, mathematically, we can take that into account by saying there's an imaginary part to the polarizability, just like in classical optics, where the imaginary part depends on the line width or the spontaneous emission rate in the excited state. So if I were to look at the effective Hamiltonian as having a Hermitian part, or a real part, and an anti-emission part, or an imaginary part, then the real parts depend on the light shift, and the imaginary part depends on the rate of photon scattering. And the rate of photon scattering here depends on the intensity of the light, which is proportional to the square of the electric field, or the Raman frequency, and it falls off inversely with the detuning from resonance. Okay? So, notice here this dependence on detuning. Remember, see, typically when we say, June mentioned optical lattices in his talk. An optical lattice is an optical dipole trap where you detune far from resonance and produce a light shift that is a lattice, which can trap atoms. And the way that works in the Corey works, you tune very far from resonance because the light shift only falls off like 1 power of the detuning, whereas the scattering rate falls off like 2 powers. So if you detune far enough, with enough power, you can get a coherent trap with little heating or loss. Oops. I don't even know if this is on. Is it on? No. Okay. No wonder my throat is so dry. I'm such a loud mouth. All right. So, now, if we want to make use of this tensor light shift, we might say, let's just detune really far from resonance and crank up the intensity. But we just said if we do that, if we detune too far compared to the hyperfine splitting, then we lose the tensor effect. So that kind of limits us, and we'll see that, maybe, I don't know, in Paul's talk. But it is something to keep in mind, that the tensor light shift cannot be meaning arbitrarily large compared to photon scattering. Neither can the vector, for that matter, but the strength of tensor versus vector depends on the ratio of the fine structure to hyperfine structure splitting. And the fine structure splitting is so much bigger, you can make the vector shift huge. Okay. So, we're on to the last big chunk of the talk. And now, this was given out as an option at the beginning, but no one took it up. Do we want to take a mini break? Or continue on?
I think a break is convenient.
Okay, we'll take a mini break. You tell us, the chairperson, how long our break should be.
6 minutes and 23 seconds.
Okay, I got the iPhone. I'll ask Siri to do it. All right, we'll come back very soon.
5 or 10 minutes.
Okay.
But I think it's good to have a break.
Let's do that. Oh, excellent. Oh, fantastic. Yeah, absolutely. It's very arcane. I've never it's like a but it's not absolutely real. It's all the definition you're talking about. Looking at the way it's an efficient field, that's exactly what this is. Everything is here. That's It corresponds to the
Right. You're almost there.
you don't have so you might have your oscillator, but there's maybe air.
We're getting home,
So what we're saying is that happens when you can atom alone, ignoring the high scale.
She's not really large tensors. But what's interesting is this business we've been doing the 7. So the tensor shape is actually quite large. It's a fine structure.
So you can use STAMP for quantum statement if you want an arbitrary unitary transformation. That combination of vector and tensor is enough to eliminate any kind of arbitrary that a general scale will not even take it's not the best.
Photon has You have to know that it's there, and then you have to know how to get rid of it. Then you have to be more clever. You have to know how you accomplish or to get rid of it. When it comes to the question, does it have an effect? from our end. And then you allow yourself to go below that scale and then the entire round. Sure. That's what ensures that you don't just want to equals 4 and equals 3. You want 1 to 0. In a way that's exactly equivalent to the rotating equation. But if you can combine two equations.
So are these two manipulations, are they from
Once you're done with correlation,
That's something to say.
yeah.
Say from the top of like that's what you
I mean, it really is going to depend.
So,
Yeah, I think for the case of the first retrievable,
is
using the tensor like shit,
you
really want to see
the random ratios and an average scale of
All right, folks, maybe we'll get started again. I can get this thing to work. Let's see. It looks like it's working. Okay. I don't know why it's red, but maybe it's running out of line. All right. Anybody have any questions before we continue on? Please feel free to pipe up. All right, so we now have kind of our control toolbox that we're going to be considering. And now the question is how we take that to apply this to some interesting quantum control task. And what do we mean by that? Well, again, in the same way that we talked about this from the classical point of view, there are sort of two paradigms that one thinks about often in quantum control as a kind of open loop and closed loop quantum control. And in open loop, just like getting, from my house to the airport, one thinks about some known dynamics, in this case perhaps Hamiltonian dynamics, which in some abstract space provide some kind of, for example, landscape, and I want to, find my path in some notion of optimality from one to another. And so one needs to design the controls based on your best knowledge of the dynamics available. There are other paradigms thinking about this from the point of view more analogous to the feedback control that one sees in the classical engineering context, whereby one, say, does a measurement of a quantum system. In this case, this is a picture taken from Sergei Rosh's. Google will get you anything. Nobody owns anything anymore. Probably not even your own social security number, but who knows? Whereby circular Rydberg atoms are being, put through a cavity, and then one measures the atom, and then one shines back in microwave radiation, say, conditioned on a measurement that one does. So these are different paradigms, and they're both interesting. This, of course, has some aspects of quantum measurement. We're not going to be talking about feedback control in my talks. I don't know if we'll hear about it from anyone else. We will talk about quantum measurement and quantum measurement back action in my second lecture. But what I want to focus on today is this picture of open loop quantum control. Okay, so the first question because, you know, as Pierre mentioned, physicists love jargon. Everyone loves jargon, I guess. There's this notion of what's called controllability for a quantum system. And in this case, what we're talking about are closed quantum systems, systems that are described by Hamiltonian dynamics. And what we mean by controllability is that in principle, we can make an arbitrary unitary time evolution operator for the system using whatever Hamiltonians you have. So the Hamiltonians is what you got in your toolbox. You're going to bring them out, throw them at the system as much as you can, and you say, can you, with the Hamiltonians that you got, and you know, based on the Schrodinger equation, can you implement whatever unitary transformation you want, time evolution operator. T here is the time ordering operator for our usual time-dependent Hamiltonian. Now, one thing to note is that, you know, it's not trivial to say what this Hamiltonian is because of this time dependence. I can't invert this equation because of this time ordering operator in any easy way whatsoever. If this was a time-independent Hamiltonian, well, that's easy. I just take the log of the matrix, divide by t, and there's the Hamiltonian. And if I had that, woohoo! But, you know, I don't have that. So I got what I got. I got those magnetic interactions, I got this logic, I got these great tensors, but I don't have maybe whatever. All right, so this is the question of unitary controllability. With the available Hamiltonians in my control toolbox, can I generate an arbitrary U of t? And I'm going to ignore what there are perhaps practical constraints of how much time it takes and how fast I have to change things, what my slew rates are, what my bandwidth is, all of that. That, you know, in the theoretical discussion to start, we're going to ignore. Okay, so here my Hamiltonians inside are, well, you know, I have some perhaps free or base Hamiltonians. I have what we call the control Hamiltonians, which can be modulated in some way with the knobs in the laboratory based on classical fields. Okay, so those fields at the moment, my magnetic fields, my light fields, we're treating as classical fields. The atoms are quantum. So the answer to this question is a question from group theory. So for a Hilbert space, in this case we're considering Hilbert spaces of a finite dimension. They say we're my 16-dimensional Hilbert space for the cesium atoms. The system is said to be controllable if this set of control Hamiltonians generates the Lie algebra of the Lie group of unitary matrices of dimension D. Okay, that's the statement which we're going to explore now for the remainder of this lecture. So I should note, you know, typically we don't care about the overall phase of the quantum state. And so if that is considered to be irrelevant, then quite often we look at this set of special unitary matrices, the one of determinant 1. And in which case we think about the group SUD, which are generated by traceless Hamiltonian matrices. So it's a minor point, but I'll come back to that. So let's start developing a little bit of intuition about some of those words, which maybe not all of you are familiar with. So let's say I want to think about controlling things on a two-dimensional space, or equivalently, any irreducible representation of the group of rotations in quantum mechanics SU2. You remember the rotation matrices in quantum mechanics are generated by the components of angular momentum, be they orbital or spin. And so an arbitrary rotation matrix could be thought of as an exponentiation of, say, in this case, written in an axis angle parameterization. So these set of matrices, you remember, are defined the group SU2. And the algebra of the group are the things in the exponents, the generators of the group. In this case, the components of angular momentum. And that algebra is a vector space because if you add two matrices together, you get another matrix in the same algebra. And it's a vector space of dimension 3. And it's also defined by these commutational relations. These commutational relations are important, as we'll see in just a little bit. So, one talks about the generators of the group. What do I mean by the generators of the group? So, for example, the algebra always has the little letters, the group has the big letters. So, the algebra SU2 is generated by these two matrices or operators. And what we mean by that is the following, that I could make any rotation in this group just based on some rotations generated by either this or that. So, for example, you may remember the Euler angle decomposition. You know, why the heck do you learn the Euler angle decomposition? I don't know, but we do. And that you remember that there are these three Euler angles, and I can make an arbitrary rotation based on, you know, first rotate around y, then rotate around, that should say z, oops. Then rotate around z, then rotate around y. Okay? So I can make an arbitrary rotation in any direction just based on rotations around z and rotations around y, because they don't commute. So one way, another way of looking at it, suppose that this rotation was pi over 2, and this was minus pi over 2. Then it's like conjugating a jz with a pi over 2 rotation, which, you know, I can put these exponents into the exponent. That's a trick of unitary matrices, and then change z into x. So I can make a rotation around x with a combination of a rotation around z and a rotation around y. So I can make any rotation with just these two pieces. So these two pieces are said to be an example of generators of the algebra and therefore the group. I wanted to just emphasize here that this is true no matter what J is. So if I had a spin 7/2, this would be an SU2 matrix in that Hilbert space. Remember, or maybe you've heard of this notion of an irreducible representation of the group. It's not just 2 by 2 matrices. Even though this is SU2, it's still SU2 on an 8-dimensional Hilbert space, because it's a rotation on that spin. It's just like a geometric rotation. Another piece of intuition about this notion of generators of a group and generators of an algebra is the Baker-Campbell-Hausdorff theorem. So a group, of course, is that you take two elements of the group, use the group composition law, you get another element of the group. So here I have, say, some element of the group I've written this way, another element of the group for, I look at, you know, these H's could be considered to be Hamiltonians. And they're, say, in this case, time independent. If I turn this one on and then I turn this one on. If I combine them, then the Baker-Campbell-Hausdorff theorem says that, well, the combination, this is some other exponentiation, but the way in which I combine H1 and H2 together is through this infinite set of multiple commutators. So there's a term that's just the addition of these two terms, but then there's a correction that's quadratic in T, that is the commutator. Then there's a cubic term, which is the multiple commutator, and then there's a quadratic term, etc., etc., etc.
All possible.
All terms are here. Now, of course, in the limit that T goes to 0, if I thought about this as an infinitesimal, then I can think about this as a convergent power series. And that's what we sometimes call the Trotter expansion. If I think about very short pulses, then I can, for example, just generate one commutator, because I might say neglect the cubic term. But the point here is that what the Baker-Campbell-Hausdorff theorem tells us is that any set of linearly independent matrices generates a Lie algebra if repeated commutators span the space. So that is a test for controllability. The test for controllability is, do your Hamiltonians, which don't commute with one another, if you keep taking the commutator, then the commutator of that commutator with another Hamiltonian, and you just keep building it up and up and up, do you span the space of all operators in the algebra? So for example, the simple case that we saw is that if I take any two orthogonal directions of J, they are generators of the algebra SU2, because the commutator of Jx with Jy is Jz. And Jx and Jy and Jz span the space of an arbitrary rotation in 3 dimensions. If I had Jy and Jz, or Jx and Jz, any pair would do it. So if I was given a Hamiltonian in which I had control waveforms that I can turn on and off in an arbitrary way, then, or I can modulate, then this system is said to be SU2 controllable. And I can make an arbitrary rotation through some choice. And not a unique choice. There's many, many, many choices of that waveform, all of which do the same control task. So, how do we do that in the lab, for example? We talked about the magnetic interaction as one of our control tools. And if we, say, had two sets of coils, which made magnetic fields in the x direction, the y direction, and we can modulate the current in these two coils, then we can make an arbitrary SU2 rotation in the space. Okay? And in fact, we don't need arbitrary modulation of the magnetic field. It's enough to keep the magnitude of this vector constant and just rotate the direction of the magnetic field. So I have a magnetic field which is rotating back and forth in some crazy pattern in the xy plane, and in principle that will allow me to rotate, perform Larmor precession around an arbitrary axis. Now that is not an arbitrary unitary transformation on the space of F. Remember, suppose I had F equals 3. F equals 3 had 7 sublevels. I can't get, say, from M equals 3 to M equals 0 by a rotation. There's no SU2 rotation that can do it. There's some rotation in Hilbert space, but it's in the space SU7. It's not in the space SU2. And this doesn't generate the space SU7 because the commutator algebra closed. We got Fx, Fy, Fz, and that's all we got. So we want to do control, we need more. And we got more. One of the things we got beyond this magnetic interaction is we talked about the light shift interaction, which had generally a scalar term, a vector term, and this tensor term, assuming these coefficients C0, C1, and C2 are all non-zero. Now, if we're talking about control on a given subspace with a given total F, the identity doesn't do anything, so I can ignore that. This term also, remember, F squared is the same on all the magnetic sublevels. It's FF plus 1 times the identity. So those terms are not important. If my light is linearly polarized and the lab is really